we're given a set A with 5 elements and a correspondence defined in this set with this binary matrix. Remember, the binary matrix means, or is marking with ones, the pairs that belong to the correspondence, okay? So 1, 1 is in the correspondence, 1, 2 in the correspondence, etc. I'm denoting the elements of A, 1, 2, 3, 4, 5. You can use letters or whatever. 1, 2, 3, 4, 5, okay? For this is the first position, this is the second position of the pair. And we need to prove for this correspondence that is an ordered relation. That's the first thing. The second, we need to find the domain and the range, then draw the Hasse diagram, and find a topological order containing R. Okay, let's begin with A, right? Proving that it is an ordered relation. We need to check that the 3 properties hold for this relation. We need to check that in the binary matrix. Reflexive is the easiest one because all we need to check is that the diagonal is made of ones. There's no zeros in the diagonal, which is the case. So reflexive is okay in this case. Then antisymmetric. For antisymmetric, we need to check that if Mij is a 1, then Mji is a 0. So, and this is when I and j are different. So we need to go to the off diagonal ones, like this, right? And check that for every one that you have here, in the symmetric position, you have a 0. So this is a 1, this is a 0, that's okay. 1, 0, 1, 0, 1, 0, okay. Then you also have 1, 0, 1, 0, 1, 0, 1, 0. That's okay. So it's antisymmetric. For transitive is perhaps the most complicated. What you have to do is to look for the off-diagonal elements again and look for the ones. So here we have a 1 in the position 1, 2, 1, 3, okay, and 1, 4. These are these 3. Then we have 2, 3, and 2, 4. Right? 2, 3, and 2, 4. Then you also have 3, 4. There's no one beginning with 4, and then with 5 we have 5, 3, and 5, 4. Okay, these 2 ones. And now we have to check that if Mik is a 1 and Mkj is also a 1, then Mij is also a 1. This, we have to check this for all possibilities, all possible numbers here. Okay, let's see that. We have 1, 2, right? Now we go for a 2 here in the left position. We have a 2, 3, so we must have 1, 3. Yes. We have 1, 2, there's another 1, 2 here, so there's 2, 4, so we must have 1, 4. Okay. And there are no more 2s in the left position. Then we go to 1, 3. And we look for 3s in the left position. We have 3, 4, that's the only one. So we must have 1, 4. Okay. Now we go to 1, 4, but there are no elements with a 4 in the left position, so that's okay. Then we have 2, 3. Go for the 3, 3, 4. So we must have 2, 4. It's okay. We have 2, 4, but no 4 in the left position, so that's okay. Same for 3, 4. Then we have 5, 3. Go to this 3, 4. So we must have 5, 4. That's okay. And 5, 4 is okay because there are no 4 in the left position. So yes, this holds for every case. So it's also transitive. So that proves it's an ordered relation. Now the domain and the range are trivial in an ordered relation because it is reflexive. Reflexive means that AA is in the correspondence for all A in the set. And that means that the domain is, and the domain of R, which are all the elements that can appear in the left position, and the domain of R, sorry, and the range of R, which are all the elements that can appear in the second position, are the whole set A. So that's trivial. But this is true for every order relation or every equivalence relation because they are reflexive. Any relation that is reflexive must have this property. Okay. Then we need to find a Hasse diagram. Okay. For a Hasse diagram, we need to take the set 1, 2, 3, 4, and 5. Okay, and look for elements which have no smaller element than them, right? So that means that if we look at these elements here, or these ones that we have here that mark the relations between these elements, between different elements, we have to look for those which do not appear in the right position. Okay, so 1 does not appear in the right position, so 1 is a minimal, and 5 does not appear in the right position, so 5 is another minimal. So these are minimals of the set A. Okay, so these are the 2 elements that appear at the lowest position in the Hasse diagram. Okay, now we remove them, right? We remove this. Okay, so we remove the 1 and the 5. We're left with 2, 3, and 4. And we also must remove the corresponding relations from here, so we are left just with the M23, M24, and M34. M34. Okay, and again we must look for elements which do not appear in the right position, and the only one is 2, so the next one is 2, right? So 2 is here. Now you see there's 1, 2, so there's a line going from 1 to 2, and there's no 5, 2, so there's no line going there, right? Eliminate the 2, and we eliminate these 2 elements, right? So we're left with just this, and the 3 is the next minimal, so we write the 3, but we're going to write it here. Okay, let me put it here, 3, and then 5, 3 is a line, and 2, 3 is another line because it's here, right? And once we remove the 3, the only element left is the 4. So we have the 4 here, okay? And we have 3, 4, so there you go, 3, 4, right? Okay, so this is the Hasse diagram of this set. Finally, about the topological order, but we have to find an order that is compatible with this. Now, 1, 2, 3, and 4 are ordered like this. So 1 is smaller than or equal to 2, smaller than or equal to 3, smaller than or equal to 4. So we just need to place the 5 somewhere in a way that is compatible with this. So which means has to be smaller than 3. So why not including it here? So that's it. This is a topological order. Okay, because if 2 elements are ordered here, are also ordered like this, right? And this is linear. Okay, so that's it.